Assalamualaikum warahmatullahi wabarakatuh and very good morning. I hope you are all keeping well. We are doing our lecture online again today due to the COVID-19 situation. Things have become a little bit, quite a lot worse these past few days. So let's just continue with our lesson and hope that this situation going to be improved for all of us. This is my first recorded lecture on CHM676, but I have met my students a couple of times before this, and went through a few of the basic introduction to organometallic compounds. So I am going to go through some revision of the earlier topics and then in detail of some of the more involved topics in this lesson. My name is Hadaria Bahrun and I am teaching CHM676, which is organometallic chemistry for this semester. As an introduction, you're very well aware that organometallic chemistry is sorry, I'm trying to make it bigger. Is it better? Yeah, organometallic chemistry is a branch of chemistry that bridges the organic discipline and the inorganic or metallic discipline. And for organometallic chemistry, it is concerned with complexes containing metal to carbon bond. So the definition of an organometallic compound is any compound that has metal to carbon bond. So this is a very important definition that you must be aware of. So we're not going to deal with any compounds that have not any metal to carbon covalent bonds. Even if your compound contains organic ligands, but if the bonding to the ligand occurs through oxygen, sulfur, nitrogen, or phosphorus, like you will typically encounter when you talk about coordination compounds, those are not organometallic compounds. Half of the world's research publication, more than half of the world's research publication in chemistry are currently on organometallic compounds. One of the most important classes of compounds in the 21st century. Why do you think that is? Because why are organometallic compounds very important? Because they are they benefit the industry because they have a very good potential to be a catalyst. Towards the end of this lesson, towards the end of CHM676, you will understand how organometallic compounds act as a catalyst. So I am going to do a little bit of introduction. Many Nobel Prize winners of chemistry come from the discipline of organometallic chemistry. So Grignard, Ziegler, Fischer, Wilkinson, Fukui, Hoffman, and a few other more recent Nobel Prizes have been won. So for any scientist to win Nobel Prize, this is a tremendous achievement indeed, where their findings have proven to change the course of human life to the better. They improve, all of their findings improve the quality of human life. So these people who have won Nobel Prize have actually contributed tremendously in the well-being of the human population or human life on Earth. The most simple or the simplest organometallic compounds would be the carbonyl complexes. The carbonyl complexes are metal which are bonded, metal centers bonded to carbon monoxide ligand. Yeah, carbon monoxide ligand. So when you have a carbon monoxide ligand CO, and that ligand attaches itself to a metal center, then you call that a carbonyl complex. So carbon monoxide acts as a pi acid ligand. I will tell you why it will act as a pi acid ligand. Acid means accept electron, yeah? So pi acid ligand or a pi acceptor are very, very important in the world of organometallic chemistry, because the reason why they are called pi acid ligand, because they are capable of accepting an appreciable amount of pi electron density from the metal ion into an empty pi to pi antibonding molecular orbital. This may not make much sense to you at the moment, but as I go on this lecture today, I'm going to explain to you how carbon monoxide is bonded to metal, and you will understand this perfectly, hopefully. So carbon monoxide is an ideal pi acid ligand. It is defined, the definition of pi acid ligand is any ligand that can accept, remember acid is accepting electrons from electron-rich metal into the empty molecular orbital. And obviously for empty molecular orbital, it has to be the lowest occupied, at the lowest empty molecular orbital that has the type pi. So pi type, if you recall your CHM574 or 477, you will understand what do I mean by the pi type. But never mind, I'm going to do a little bit of revision a little bit later, so that you can refresh your memory on this. So carbon monoxide provides a model for bonding of pi acid ligands to metal. The stability of carbonyl complexes can be described in terms of back bonding between metal M to the pi antibonding LUMO of the ligand and the so-called pi acid behavior. Ligands with this behavior are commonly known as pi acceptors. Yeah. The well-established synergistic bonding mechanism of carbon monoxide to metal consists of actually two plus one very important criteria. First is the pi donation from carbon monoxide to metal, followed by pi back donation from metal to carbon monoxide. So those are the most important two components. And the characteristic of this sigma donation, did I say pi just now? So I was wrong. The sigma donation from carbon monoxide to metal and pi back donation from metal to carbon monoxide, these two occur synergistically. Synergistically means that they happen at the same time. One will make the other stronger. So sigma donation makes pi back donation stronger, and vice versa, the pi back donation makes the sigma donation stronger. So before we go any further, I would like to refresh your memory on this topic that that have been discussed in inorganic chemistry 2 CHM574. So as a little bit of a revision for carbon monoxide molecule, when we talk about heteronuclear diatomic molecule, you will realize that all the orbitals of oxygens lie at lower energy than the corresponding ones of the carbon atom. Yeah, here, let me show you this. Yeah, this is on the right side here is the atomic orbital of oxygen. On the left side here is the atomic orbital of carbon. So because oxygen is slightly heavier, having relative atomic mass that is higher than carbon, all of the the 3Ps are placed or are located at the lower energy level compared to the S and the 3P of the carbon. Carbon is lighter, so it is the energy level of these orbitals are higher. Oxygen is heavier, so the energy levels of these orbitals are lower. So because of the mismatch of the energy levels, the 2S no longer exist at the same energy level as the 2s of carbon. The 2s of oxygen, 2s of carbon, they do not exist at the same energy level. So there is no effective overlap in terms of overlap. There is no effective overlap between the 2s of oxygen and the 2s of carbon, because if, okay, as you can recall, the shape of s orbital is uh, spherical, sphere, circular. So when you have one is located higher energy than the other, when the carbon and the oxygen atoms approach one another, the matching of energy does not happen. So the 2s of carbon and the 2s of oxygen do not overlap. So there is that is the reason why this 2s of oxygen becomes a non-bonding molecular orbital. Non-bonding means it doesn't make a proper bond. It doesn't contribute into the bonding of carbon to oxygen, and it is called the sigma. So you might also recall that in CHM574, in molecular orbital, you do not talk about S and P anymore. You talk about sigma and pi and delta. Yeah. So in molecular orbital, the ones in the middle are the molecular orbital of carbon monoxide. The 2s becomes sigma 1, which is a non-bonding. Why non-bonding? Because there is no effective overlap. Atomic orbitals do not overlap effectively, so it becomes a non-bonding. However, your 2s of the carbon has the right geometry, or has the right orientation and the right energy to overlap with the 2px. Now, if you can recall, the shape of a 2px is a dumbbell shape on the x-axis. Yeah, do you recall that? Dumbbell shape on the x-axis. This is a round atomic orbital. This is a dumbbell shape on the x-axis. So there is a good overlap between the 2s of the carbon with the 2px of the oxygen, making two molecular orbitals. So two atomic orbitals overlap, make two molecular orbitals. There's no more, no less. When you have two orbitals overlapping, you get two molecular orbitals formed. One is called a sigma bond, another one is called a sigma antibonding bond. Antibonding is denoted by this asterisk. Yeah. Now, so the overlap of 2s and the overlap of 2px make a sigma 2. It is called sigma 2 because there is a sigma 1 already at the bottom here, arising from this 2s orbital of your oxygen. So sigma 2 is a bonding molecular orbital, and this is the interactive. This is in phase overlap, and this is out of phase overlap. So you get sigma antibonding. So we call it sigma antibonding 3. We go up sigma 1, sigma 2, sigma 3. So this is your molecular orbital 4 that is produced through the overlap of the 2s of carbon and the 2px of oxygen. Now, what do we have left on the oxygen? This have become sigma 1. That has become sigma 2 and sigma antibonding 2. So you only have these two unreacted or unaccounted for at the moment. So you have, this is 2py and that is 2pz. For 2py and 2pz to overlap effectively, they have to be matched with 2py and 2pz of your carbon. If the 2py and 2pz were to overlap with the 2px, is not going to overlap effectively because the orientation is wrong. So you have 2py of the oxygen overlapping with the 2 excuse me, of the 2py of the carbon, and then the 2pz of the oxygen overlapping with the 2pz of the carbon. So because the overlap, if you look at the shape of 2py is on the y-axis, overlapping with another y is a side-to-side overlap. Previously, when you see sigma, you have a head-to-head overlap. This is a recap of CHM574. So a side-to-side overlap produce pi bonds. So these two react with these two or overlap with these two to produce two pi bonds, uh, 2 pi bonding molecular orbital and 2 pi antibonding molecular orbital. So this is we call pi 1, and these two we call pi antibonding 2. And lastly, if you keep track, this is still unreacted with anything. So this cannot react with anything else in here because everything here is accounted for. It just simply goes to become another non-bonding molecular orbital at the top. So we have sigma 4. So these are the molecular orbitals of carbon monoxide. Now be very, very careful and be aware of this formation of this molecular orbital. Now look at the electrons. On carbon, you have 4 valence electrons. Is that familiar? If that's not familiar, then you'll be in much trouble. In the oxygen, you have 6 valence electrons, so a combination of 4 and 6 make 10 valence electrons that you have to place on this molecular orbital. So you put the electrons into the lowest energy level orbitals first. So obviously sigma 1 is the lowest energy level, followed by sigma 2, followed by pi 1, 2 of them, followed by sigma antibonding 3, followed by the pi antibonding 2, and then the sigma 4. So when you add 10 electrons into your molecular orbitals, 2 will go and make fill this sigma 1, another 2 will go there, and then this degenerate pi 1 will be filled 1, 2, and then after the 2 are half filled, another one comes in to make a pair 1 and 2. So you have 2, 4, 6, 8, and another 2 have to be placed on the sigma antibonding 3 because this is the next energy level that is available. So you have, I think you can also recall from your 574 that this is your HOMO, highest occupied molecular orbital, which is, as it says, the molecular orbital that is occupied the last. And then you have this one, this 2s, which is designated pi antibonding 2. They are called the LUMO. These are your lowest unoccupied molecular orbital. So pay attention to HOMO and LUMO because these are the orbitals that will participate actively in bonding with metal. These 4 molecular orbitals will not participate in bonding because they are too stable. The energy level is low. They're too stable to participate in bonding. Only the HOMO and the LUMO will participate in bonding. This one at the top here will also not participate in bonding because the energy is higher. This is not the LUMO. So having gone through that revision of formation of molecular orbital of carbon monoxide, you are ready to identify these things. Yeah. Yeah, these things. The sigma 1 is a non-bonding. There is no atomic orbital contribution from carbon, but all of it comes from the oxygen. So we call this a non-bonding molecular orbital. The bonding would be your sigma 2. This is just a recap of formation between the overlap of 2s and 2px, as I was going through with you just now. The sigma, the pi 1 is a bonding molecular orbital, the result of overlap of 2py on carbon, 2pz on carbon with 2py, 2pz on oxygen. The sigma antibonding 3 is an antibonding molecular orbital. This is the opposite of this one here, from the overlap of 2s and 2px. The pi antibonding 2 is the also antibonding molecular orbital. This is the opposite to what's happened at the top here. This is a bonding, this is antibonding. And lastly, the sigma 4 is the 2px of the carbon and no contribution from the oxygen. Yeah. So that's just that. So having known the molecular orbitals of carbon monoxide, and I've told you that HOMO and LUMO of this will be participating very, very actively in bonding with metal, you're now ready to see how carbon monoxide bonds to metal. Now, carbon monoxide is a ligand that forms complexes with most transition metals, forming metal carbonyls, which are very useful starting materials for the formation of organometallic complexes. The principal way in which a carbon monoxide molecule forms bond to metal is in a linear MCO fashion. Obviously, you have a linear situation happening there. The first step to bonding of carbon monoxide to metal is when you have, this is your HOMO, highest occupied molecular orbital on CO. Your HOMO is a sigma bond. Yep. No. Your HOMO is a sigma antibonding. HOMO is the sigma antibonding. This is the shape of your sigma antibonding on CO. It will overlap with a hybrid orbital on the metal, and the overlap will be head-to-head overlap, making a sigma bond. So this plus this makes that. So this is your hybrid orbital in metal. This is your sigma antibonding 3, HOMO on carbon monoxide. This will approach that, or the other way around, metal will approach carbon monoxide, and upon an effective overlap, there will be a sigma bond formed between the metal to carbon like this. The property of a sigma bond is the concentration of electron is between the two bonded atoms. Yeah. So that is the first step, which is the formation of the sigma bond through the overlap of HOMO on CO with the hybrid orbital on metal. Now, electrons, electron flow from carbon to metal here, the electron. This is the filled orbital, this is the empty orbital. So obviously, the electrons, why do I say it is filled? Because it is here, it is full, yeah? So those two electrons will be shared with this metal, and this bond is called a covalent sigma bond, where the electrons come from carbon only. There is no contribution of metal in terms of electrons in here. So the electrons will flow from carbon to metal and will make a dative overlap or a dative covalent bond that would lead to an unacceptable high concentration of electron density on metal atom. Now, as you will recall, metals are electropositive elements. They do not favor having too much electrons in them, because for metal to achieve octet or to imitate the noble gases, they do not need electrons to be put in them. They need to lose electrons. Yeah. So having carbon contributing or giving electrons to metal will be leading to a situation where electron density of the metal ion is the metal atom is very, very high. And by nature, when there is a high electron density on metal, the metal, which is electropositive, will attempt to reduce the charge by pushing electrons back to the ligand. So electrons will flow from here to there, and then this will become too high in electron density. So what it will do, it will push electrons back to the ligand, and this is made possible only if the LUMO of the ligand has suitable is of the same orientation as the orbital in the metal. So this is called a pi back bonding. Now the second step, the first step was the formation of sigma bond. The second step is the formation of a pi bond through pi back bonding. So that is the shape of your LUMO in carbon monoxide. So have a look at your LUMO in carbon monoxide here. Those are your LUMO, and it is a pi antibonding. If you recall 574, any antibonding molecular orbital will have a shape similar to this, where the electron density is not concentrated between the two bonding atoms. The electron density is concentrated outside of the space between the two bonding atom. So this is the shape of your LUMO, and in metal you have a suitable shape of orbitals to interact with this LUMO. If you recall, this looks like a it looks like a dxy or dyz. Yep. So when electrons are too full in here, recall from the first step, the electron density is too high on the metal, it will attempt to push electrons back into the carbon monoxide through the overlap of the hybrid orbital in metal with the LUMO. So this is your LUMO. So when plus orbital and plus orbital overlap sideways at the top and the bottom, you get pi bonds formed between metal to carbon. So there is a sigma bond here from the first step, and there is a pi bond here from the pi antibonding. So effectively, the bonding between metal to carbon is a double bond, effectively. Now you have understood the formation of sigma bond in the first step, and you have understood the formation of a pi bond in the pi back bonding mechanism in the second step, and the drift of electrons from carbon monoxide ligand to the metal in the sigma bond will make the CO slightly positive, yeah, because electrons move away from there. When it becomes slightly positive, it will enhance the acceptor strength of the pi orbitals, because this is less electron, this is very, very rich in electrons, so it will make a flow of electrons from metal to carbon. At the same time, the drift of metal electron into the CO bond, which is referred to as back bonding, tends to make CO slightly negative, enhancing its basicity via the sigma orbital. Thus, up to a point, the effect of sigma bond formation, now this is very important, the effect of sigma bond formation strengthen the pi bond and vice versa. The formation of pi bond strengthen the sigma bond. So this kind of bonding mechanism is called synergic. Synergic means one make the other stronger and both happen simultaneously. So when you have synergic situation, you have a very, very strong bond between metal to carbon. And this is actually the explanation of carbon monoxide poisoning. Recently, we were shocked by the death of um, how many? Three or four girls, because they were found unconscious in their car because of carbon monoxide poisoning. Why is carbon monoxide lethal? Carbon monoxide can cause death because it has very, very high affinity to the iron in the hemoglobin. If you recall, hemoglobin is our the vehicle for oxygen transport and carbon dioxide transport in the body. Hemoglobin will take in oxygen from the lungs, take it to the cells, and from the cells it will carry the carbon dioxide back into the lungs and exhaled. Now, when carbon monoxide is present, the sixth position of iron, the sixth bonding position of iron in hemoglobin will be occupied by carbon monoxide. And through this mechanism, we understand that when iron bonds with carbon monoxide, iron is a metal, when it bonds with carbon monoxide, it makes an extremely strong bond because of this synergic effect. The sigma makes pi strong, the pi makes sigma strong. So metal or iron bonds very, very strongly. In fact, it is 220 times stronger bond between metal to carbon monoxide compared to metal to oxygen. So when you have carbon monoxide sitting on the iron of hemoglobin, that hemoglobin is no longer available for the transport of oxygen into the cells. So if too many of the hemoglobin is being poisoned by the carbon monoxide, poison means carbon monoxide sits on the hemoglobin, then there is no oxygen transport. Even though the girls were breathing, they inhale and exhale oxygen gas, inhale oxygen gas. Oxygen cannot bond with the metal because it has been occupied by the carbon monoxide, and over time the cells of the human cells will be deprived of oxygen. And you know what happens when there is a deprivation of oxygen? There will be asphyxiation. Asphyxiation means tercekik macam tak boleh bernyawa. Even though they inhale and they exhale, the oxygen doesn't reach. So that is why carbon monoxide being very, very lethal to human being, because of the strong bond between the metal to carbon monoxide. Yeah, this is the explanation. Okay, I hope you understand that. I'm going to stop here. I'm ready to meet you in class. So see you later. Assalamualaikum. Take care.